Hello there, my name is Rodion Ishmakov and we'll talk about projection aplanatic lenses known as bokeh monsters among photographers community. Besides the Petzval lenses, which are very famous, I'll highlight for the first time the particular type of projection aplanat which was designed in early 30s by Robert Richter. Joseph Petzval is an Austrian optician, known as a guy who used several artillerymen to compute his lens. The main contribution of Petzval to the optics development is the first successful realization of analytical approach in lens design. Also, Petzval formulated the condition of field curvature correction. The inventor of wide-angle Pleon and Topogon lenses, Robert Richter, started his career in Voigtlander in 1914. He joined Gerz in several years before it was consolidated with Zeiss. It is intriguing how the former head of Carl Zeiss photographic division has no photos in the public access now. So, photographic lenses with lack of field curvature and astigmatism correction called aplanats. Field curvature is a kind of aberration when the lens forms focused image not on plane but on spherical surface. The radius of the sphere named Petzval radius. It could be calculated from surprisingly Petzval sum. If lenses with large refractive index and low power are used in a thin lens system, Petzval sum tends to be near zero. Besides field curvature, field shape is also affected by astigmatism. This aberration causes a difference of focus's position of sagittal and tangential rays, so the Petzval sphere splits in two complex-shaped surfaces. All the aberrations are corrected considerably well in anastigmats only. A field shapes for aplanat and anastigmat with same parameters are shown on the diagrams in the right in same scale. Every colored line in the bunch corresponds to certain wavelengths in the range of 400 to 700 nanometers. One can see aplanat has such plane field as an astigmat in 1/4 part of angle. We will consider the exact difference in the design of Petzval and Richter lenses. These pictures illustrate construction of lenses described in given patents. In the left, post-war Petzval lens, in the right, pre-war projection lens from Richter's patent. This Petzval lens uses 4 different glass types, including lanthanum crowns and dense flints. The thin air space between third and fourth lenses is so-called air lens, which sometimes affects on correction better than cemented surface and ordinary air space. Lanthanum glasses appeared after the war also give advantage to this lens. Because of high refractive index, it's easier to control aberrations. On the contrary, Richter lens was made extremely simple. It uses only 2 of the cheapest glass types, ordinary crown and ordinary flint. The first lens has the same radii of curvature, and the second is flat concave, which further reduces the cost of the lens. This approach to lens design is absolutely understandable. In the early 30s, Germany was not a very rich country, but the film industry was rapidly developing and required the production of more projection apparatuses and more projection lenses. The dimensions and the back focus distance are important parameters of lens. Compared to the Petzval, the Richter lens is generally longer with a significantly shorter real focal length. As you could understand, simplifying the lens design usually leads to an increase in lens size while maintaining quality. New glass helps make the lens more compact, and therefore the comparison of these two lenses may not look entirely fair, due to the different technological level. However, one should not overestimate the impact of these nuances on image quality. Let's now move on to consider the residual aberration of both lenses. The image quality at wide open aperture in the center of the frame is mainly determined by spherical aberrations and axial chromatism. These diagrams show the aberrations of focused Petzval and Richter lenses on the optical axis. The vertical axis shows the aperture value, and the horizontal axis shows the shift in focus position, that is the amount of aberration. The observed S-shaped curve is a characteristic of all lenses that combine third and high-order spherical aberration. For an ideal lens, the beam should be coincided with the vertical axis of the graph. A strong divergence of the bunch of curves on an open aperture is spherochromatism. Its level is higher for the Richter lens, but at the same time the amount of spherical aberrations in general is slightly lower than that of the Petzval. Let's now compare the field shape and the distortion level of these two lenses. As it turned out, the Richter lens has a slightly higher level of astigmatism compared to Petzval, as well as a noticeably greater distortion, almost -3%. One way to evaluate image quality is to look at the aberration spots of lenses. That is how they transform a point light source in an image. Both lenses behave similarly within a 12-degree field. Then Petzval fails in the sharpness of tangential rays and Richter in sagittal ones. You can estimate the pattern of both lenses by calculating the defocus spots. On the left are the prefocal spots, on the right are the postfocal spots, and central ones are in the image plane. At first glance, the shape of the spots is very similar. As you can see, their transverse size only increases from the center to the edge of the frame due to field curvature and astigmatism, and their vertical sizes decreases because of vignetting. This is what causes the tunnel effect of the swirling bokeh of projection aplanats. Upon closer inspection, it turns out that Petzval bokeh discs has a bright border, especially at the edge of the frame. At the same time, in Richter, the border in the center of the frame is not pronounced, and along the edge of the frame it is present only on one side of the disc. So the picture rendition of Petzval and Richter should be noticeably different. The modulation transfer function of the lens, also known as MTF, allows you to quantitatively measure image quality. It is usually calculated for two frequencies, 10 and 30 lines per millimeter, which corresponds to counter contrast and details. According to the graph, we can conclude that Petzval has slightly better image quality across the field, but Richter is at the same time ahead of the Petzval in terms of detail in the central area of the frame. The sharpness in the center is generally good for both lenses. Small format lenses usually demonstrate the maximum level of image quality at an aperture ratio of 1/8. Comparing the longitudinal aberrations of Petzval and Richter at this picture, we find that Richter has narrower secondary spectrum and less third-order spherical aberration. This affects the image quality. The Richter lens is slightly better than Petzval lens this time, as can be seen from the size of the aberration spots. The MTF curves of the lenses indicate their similarity in the optical quality level at the 1/8 aperture. So, to summarize, one can highlight that Richter lenses are extremely simple in design, use cheap types of glass, and at the cost of slight increase in size, are able to successfully compete with the more technologically complex Petzval lens with expensive glass. While somewhat inferior to the Petzval lens in terms of field quality at one wide open aperture, Richter lenses are better in the central area of the image. It is logical to guess that if Petzval lens uses same simple glasses as Richter, then the overall result will no longer be in Petzval's favor. Finally, both Petzval and Richter lenses are widely available on the aftermarket now. There are many Soviet Petzval lenses such as Lomo P4 and P5, as well as Western Petzval variants. Richter lenses become even more popular in Soviet Union and were manufactured in a large scale as a KO lenses series. The most famous Western Richter lenses are Zeiss Kypronar and Mir Kinon. Now I'd like to show some photos made on different Petzvals and Richters. This photo was taken on a Loma 92 projection Petzval. It uses cheap types of glass in its design. The picture from this lens is a soft at open aperture. Quite strong chromatic aberrations are noticeable. It also colors the border of the bokeh discs. The background swirl is almost indiscernible on this photo. And the next photo was taken with the Richter KO similar in parameters and technological level lens. The center sharpness of this lens is excellent. The bokeh has almost no fringing and is very swirly. Now just look on the characteristic shape of the lens field and delicious bokeh of Petzval 92 lens. Here we have Richter again. His pattern is much expressive and sharper than Petzval's. At the short distances, the soft effect of Petzval becomes very noticeable, as does the astigmatism at the edge of the frame. But if you close the aperture by one stop, the sharpness becomes more than enough, and the image doesn't get worse at all. At the same time, the KO lens is quite sharp even from an open aperture, although at short distances the glow effect still becomes appreciable. Another photo on Petzval 92 at aperture 2.8. Despite the slight soft effect, the texture of the petals and droplets is very clearly visible. If you try to shoot a landscape with a Petzval or Richter, then even at a small aperture there will be no sharpness at the edges of the frame. The cause is not even the field curvature, but the astigmatism of these lenses. This photo was taken on a record-breaking Petzval with parameters 120 and the aperture 1.6. Few lenses have such parameters, and even with a 4-lens design. Spherochromatic aberrations are huge here, the lens is very soft, but the quality is still sufficient for a portrait. On the contrary, long focus Richter lenses at moderate apertures turn out to be very sharp and high quality. On a crop camera, they could be used as a super light telephoto lens for photo hunting. Next shot was taken with a Canon crop camera and a KO lens with the aperture 2.1. The lens is sharp enough, even at an open aperture, to accurately detail the fur of this beautiful squirrel. Richter lenses with aperture 1.8 have usually more fringing. Here's a photo of the Andromeda with an exposition of several seconds taken with a Canon crop camera and KO 120M lens. Blue fringes are visible around the stars. They could be eliminated by slightly stopping the lens down, but at the edges, due to the shape of the field, the stars look blurry. It is worth noting that Petzval and Richter lenses are used as apochromatic telescope lenses. In this case, their aperture usually doesn't exceed 1 to 4, and the lenses are made of low dispersion glass. That's all. Comment on which lenses you like better, Petzval or Richter. Thanks for watching.